Hi, and welcome to the Introduction to Simulink webinar. My name is Ryan Gordon, and I'm here with my colleague Michael Carone.
How you doing there, Ryan?
Very good today, and we're going to be walking the viewers through a quick example of how to use Simulink for a relatively simple mechanical system.
Yep. Yeah, you're going to show a way to represent a mass spring damper system in Simulink, right?
Absolutely. So if you've gone through engineering school, you may have seen this system before. And let me start by opening up Simulink. And the way I like to do that is by typing in Simulink in the command window, but there's actually other ways to do that. What's your preferred method?
I probably type in Simulink a lot. Sometimes I just open up an existing model, or I'll click on that Simulink library button up there.
This button right here. Open up the Simulink library. So typing it in or clicking on this button will do the same thing, but as a longtime Simulink user, I tend to just like to type it in.
Probably also because I like MATLAB and I type a lot of things in MATLAB.
Yeah.
That could be another reason why I like to do it that way.
When you're an avid MATLAB user, you tend to use the command window quite a bit. All right, and so when I open up this new model, I can just double click to type in. It's much like a comment, so anything I type in here isn't actually going to affect what my system performs like, but I want to type out the equation that I'm going to be representing here. And it's x dot, and then spring constant.
And so what you got here, this is basically Simulink. You've got your library browser on the left. You've got your your editor window here on the right.
Yeah.
I mean, that's Simulink, and you're going to be dragging blocks from the library browser into the editor window to build up your model.
Okay, so b is x dot minus the spring constant k times x. So all I've done here, Michael, is I've written out the equation for a mass spring damper where you have the mass, damping coefficient times the velocity, and the spring constant times the position, and then you have a force to drive the system.
Yep.
And I've just moved some of those pieces around so that this is actually going to make it a little easier for me to design in Simulink.
Okay, so just an algebraic manipulation of the first equations.
And so on the left-hand side, here's my library browser. You see I've got a lot of toolboxes here. So working at the MathWorks, I have access to just about everything under the sun.
Right.
So if you're doing something like signal processing, HDL, code generation, you can do all that in Simulink, but we're just going to focus on the basics today.
Okay.
And the first thing I want to do is I want to generate my force. And just to show you how this all works, I'm going to grab a scope block from the commonly used blocks. I'll actually probably spend most of my time in here today. And so I can have my force, and my scope is just going to show me how my results look.
Okay.
Open that up.
So there you go. There's a Simulink model. You could press play right now, right?
Yep. And that's what I'm going to do to see how the sine wave looks. Okay.
Right.
And so
that looks like a sine wave.
Looks like a sine wave, yeah. So let's look under the hood here of the force that I'm generating, and you can see the equation that the sine wave block uses to generate that sine wave, and I can adjust some of the parameters here to change how the results of the sine wave look. So if I change the amplitude to 2, you now see the amplitude is 2.
Yep. So that's what I also like to do whenever I'm building up models. I try to press play as much as possible just to verify that what I'm building is accurate.
Yep.
And is what I expect to see as well.
Yeah, and that's the great thing about Simulink is you notice I haven't actually had to save my model yet. Right. And I can keep building this up on the fly without having to save changes. So maybe if you have a local copy, you make a change and you're not sure you want to keep it yet, you can add and remove blocks, play the model, run the simulation, and then decide whether or not you want to save and continue.
Right.
In addition to source control, of course, which is the best way to maintain changes.
All right, now what did you just drag in here?
Oh, so this is an integrator block. So this block will integrate whatever's on the left-hand side, which in this case I'll define as x double dot, and this is why I reformatted this equation, and we'll see how this works as I build up the model.
Okay.
And when I integrate that, Michael, I'm sure you can guess what's going to come out on the right-hand side.
X dot.
Exactly.
Yes.
And then I can control, click, and just drag a copy of that over to get
your x.
Exactly.
Right.
So now I've got all the states in my model
for
the mass spring damper, and that's going to let me build up my system. Okay, so the next thing I want to drag in is a summing junction. Okay, and if you're in the controls field, you probably recognize the round version of the summing junction as a feedback control, but when I'm not doing a feedback controller, I prefer to use the square version.
Okay.
but I think
I
everyone's
usually
got
stick
their
with the
preference.
round one anyway.
Yeah.
I don't know. I guess it's personal preference.
Personal preference. So if you have a controls engineering background,
Yeah.
I think people tend to like the round version. But you know, it really depends on what fits for your diagram. There's no functional difference between the two.
Sure. Yeah.
Okay, and so what I just did is I control clicked on the line here to split the signal coming out of the force block. Okay.
Now, can you give yourself a little more room by clicking on that bottom arrow? Over there?
Yeah, absolutely.
This,
That's a good reminder.
It's the model browser.
Yeah.
Excuse me. It's good if you have hierarchy in your system to browse through your Simulink model, but probably for this simple example, you don't need it, right?
Yeah. So when I split this up, you know, a lot of new users may not know this, but this is actually going to be like a copy of the line here, right? It doesn't do any mathematics when you split up this line.
So it's like that signal is just being branched and it's going into different places. It's like an electrical circuit.
Yeah. Okay. So let me drag this here. And now I need a gain block. And this is just going to multiply that signal line by a value.
Ooh.
You like that?
I always like seeing that. Yes.
Yeah.
Every time I see that automatically rotate and you don't have to do it.
And
I
again,
just like it.
yeah, just drag and drop in. And everything just breaks those lines automatically. I really like that too. It's a great feature.
Yeah.
All right, and you know, just drag my lines around and get things to look like the way I want.
Okay.
And actually, I forgot one piece here, so I'll just highlight all this and drag it over. I need to put that 1 over m. So
see, now you're just showing off, flipping it again.
let me kind of walk through what's going on here, right? So I did a lot of dragging and dropping and all that, and I'm actually just representing the system here.
Yeah.
And it looks complicated if all you ever saw was this, but it's really just a representation of this second equation here.
Mm-hmm.
Right, so 1 over m, and actually I got to rename my signal here to be more accurate. So 1 over m times the result of the force here minus b times x dot minus k times x, and that equals x double dot.
Okay.
And so that's our closed system for the mass spring damper. Right, and now I can run that simulation, but looks like we got a problem.
Looks like there are some undefined parameters.
Yep. So when I get a dialog like this, I can actually click through it to see where it's telling me the problem is.
Yeah, so it's each of your gain blocks.
Yeah, so my B, K, and M are undefined currently. So what I can do is I could define these in the block, and I could come in here and say B is 0.1, and that would solve that error.
Yeah, but you want to parameterize it.
I want to parameterize it so I can change it without actually having to change my blocks here.
Yeah.
And we've got a couple warnings here. We'll cover these before we keep moving on. So
what's it saying there?
So using a default value of 0.2 for the maximum step size.
Yeah.
And you can disable this diagnostic, or I can resolve this diagnostic by coming into the configuration parameters.
Okay.
And so that's what I'll do. So I got a couple warnings, and now you always want to address your warnings.
Yep.
Sometimes they could be a little annoying. You might say, well, my model appears to be running, or it's not a critical error, but the warnings are going to help you get a faster solution, because as you upgrade versions of Simulink or make changes to your model, solving these warnings will keep things running smoothly.
Yeah. A lot of times they have to deal with performance,
yeah,
like you said. So.
Okay, so when I open up the configuration parameters, we see some of the default solver options here. And we see we're using the variable step solver and the ODE 4.5 solver. So that's the default solver when you create a new Simulink model. We'll leave that alone for now.
Okay.
I mean, there are options for fixed step solver or different types of ODE solvers. If you're doing a physical system using Simscape blocks, you might want to use a stiff solver. But for this system, we can leave this alone. And the warning actually is trying to address the fact that I'm using this auto step size here. So it's saying the maximum step size is going to be 0.2, and I can manually change that. But this warning actually, I think I could leave this one alone for now.
Okay. This is basically how Simulink works, right?
Yeah.
It's using these different solvers in order to compute the states of each of the blocks.
Yeah. Let's come back in here again. So so what it's doing is it's saying, okay, I'm going to generate a system that can be solved by this solver, the ODE 45 solver.
And what's 4.5? That's the fourth
order and fifth
order
ODE
right?
solvers. Yep.
Right.
It's saying, well, I think I could solve this really fast in a couple steps, but I'm going to limit myself to some maximum step size, right? And so in this case, it's giving me that warning saying that step size is going to be 0.2. I won't take a bigger step than that. Although I can change this. I can make it bigger if I wanted. And it's got a minimum step size. This is the minimum step it will take. So these are just options you can work with depending on the results of your simulation. You may want to make a smaller maximum step size for a higher fidelity simulation. Okay, so let me go back to the MATLAB workspace and define my variables. I'll just say m equals 1, b equals 0.1, and k equals 0.1. And let's see how this works. Okay, and we see our MBK values over here in our MATLAB workspace. And it looks like it was able to run. And maybe I want to run this a little bit longer. Let's say 50 seconds. So it looks a little all over the place, but
looks a little jagged.
Yeah, a little jagged. So that actually comes back to our maximum step size. So having seen that, it's solving so quickly that it's skipping over some steps and saying, well, I don't think I need to make a smaller step here because I think my accuracy is good. So let me make this a little smaller. I'll say 0.
Probably that's where the dynamics are just changing so quickly.
Yep.
Right.
Okay. Let me run that. And we see we get a little bit smoother result.
Yeah, that looks nice.
Right. Again, paying attention to those warnings, I knew that was going to be a problem.
Right. Okay.
So I've got my values in here. It doesn't look too good yet. Maybe I want to play around with my values, but for now I'll leave this alone. This is going to be okay for now. If I had an actual system, I would know what my B and K values are. Right. But I'm happy with what I have. And so what I can do is I can actually create a single block out of all of this. So I don't need a scope here anymore. And I can highlight all of this. Right click. I can right click anywhere really that's highlighted. Right. I don't need to click on any particular block. Too. And create this subsystem.
So now everything's gone, right?
Right. Well, you would think so.
You spent all that time.
So I've still got my data here. And if I double click this works as it's actually just a virtual boundary.
Yeah.
So there's nothing actually different about my system when I hit that play button. So all the data's still here.
So can you open that model browser again? Because I think this will show now why you'd want to use that model browser that you had before,
sure.
Right?
Yeah.
Okay. So now you can see that there's 2 levels of hierarchy, and obviously as you're building up a more complex model, you're going to have multiple levels of hierarchy, and it's, now you can navigate through it that way. But again, I would still argue that you probably don't need the model browser open.
No, it will save us some space.
It's pretty simple, but
I
just wanted to show that.
Yeah, we have a little bit of a limited space here when we do these webinars for the viewers, make it a little bit easier for you guys to see things. So we try to keep as much space as we can while we do this. So so we've got the subsystem here, and what I want to do now is actually record some of these variables because I'm going to start making some changes that are going to affect how my system responds.
Now you went pretty fast there. Can you go back and show what you did there?
So what I did is I highlighted these 2 signals. Just held the shift key, highlighted.
Okay.
All right, I'm not going to click it because now it's going to, I'll just click it.
Well, that would unlock it,
But I just click that and log it right here in the little record button.
Okay. So now those signals are now added to the output variable that gets generated when you simulate this model. Right? Okay.
So now when I hit the play button,
I'll
get a notification that says I can now use the simulation data inspector to view my signals.
And that's because you press the record button before you press play.
Yep, exactly. Okay. So now, the scope's a great tool when you want something, I like to use the term quick and dirty. You just get a quick view of what is going on in your simulation. Right? But you're not going to be able to see what happens as you change parameters.
Right. Yeah, it's just giving the results for that one simulation.
So now I can take a look at something like my X parameter. I'll have to come back into MATLAB. I can change, say, my K value. Maybe it's, twice as big. And I can come back into Simulink, run the simulation, and make a comparison between my 2 simulations.
So it keeps all your runs within the tool.
Yeah, so it's a very easy way for me to organize all my different simulations, change parameters, and observe the results and make comparisons, right?
So how can you actually? There's the compare signals tab, right? So can you show how it actually does the comparison between the two values?
Let me see if I can take a look at X and X. Right, and so this is what we were looking at in the previous tab, but now it's got this difference area too. Right. And you can define the tolerance here to whatever you need to define it to. So it's just some default value that we've obviously exceeded here. But you can set that tolerance to whatever makes sense for your simulation and allow you to quickly take a look at all your different signals to see if they are within tolerance.
Right. Yeah, I like to use this if I'm making like little tweaks to my model, but I want to make sure that the output variables, which I'm confident about, are not changing, very significantly. And a lot of times I'll make changes to the model, just improve performance, or maybe model things in a slightly different way that's more efficient. And so that's a nice little feature to do the comparison.
So since you brought up little changes, Michael, I'm going to actually create a mask of my subsystem here so I can make those little changes a little bit easier here.
All right, yeah.
So what the mask is going to do is allow me to change those 3 parameters I have inside of my subsystem without actually having to go to the MATLAB workspace to make those changes. They'll be accessible right on this top level. So for now, I'll leave the drawing commands alone, but you could put an image in here, or you can display some text here. You can say, this is going to be my subsystem. And whatever you put in here will get displayed on the mask. And you can see, if I had like a picture of a mass spring damper, I would put that in here.
Sure.
And this is actually, for anyone who's used Simulink in the past, this is actually a brand new mask editor.
Yeah, it's a little different, but the concept is still the same, right? You're taking parameters that are contained within the subsystem, and you're exposing them within the mask itself. And so this, I think as you're typing away, the new interface just makes it easier to create something that's a bit more complex, and you could add tabs and different regions within your mask, and and just create something that's a little fancier.
Yeah, and what you might have seen me doing while Michael was talking is I put in the prompts here for the mass, spring, and damper.
Yep.
And I've got my MBK values here. And now when I double-click on it, I've got a prompt instead of going under the subsystem.
Now, you can still go under the subsystem pretty easily by you read my mind.
This is the next step, right? Make sure everything's still the same here. If you're a new user, you may not know what all of these things are doing. The mask doesn't actually change anything inside of the subsystem. It's still a virtual boundary, but now it gives me access to these parameters, right? So if I use my mass, spring, and damping coefficients here, and then I run the simulation, you'll see I get the same results. Right, because I didn't actually change anything yet. But now say I want the spring to be half as stiff, and I run the simulation, we're going to see that those changes took effect.
Now, one thing would be neat is if you take a copy of that mass subsystem, and now you can have different, basically different instances of that subsystem in your model, but I guess you would need to put it in a library for it to be a true instance. I don't know if you're going to talk about libraries.
Well, I've got a library that I'll be using in a little bit, but for now, again, the quick way to do things is just going to be I can control-click and copy the whole subsystem.
Yep.
And maybe I want to run a simulation not just with a sine wave, but I want to see what the step response looks like.
Okay.
So I can drag my scope.
I like those little alignment things too. Nice, neat model.
And I could see, okay, that's what my step response looks like. And I can see what my sine wave looks like. And, if I wanted to, even though maybe it doesn't make a lot of sense, I can compare the two, right? They look different, so that's kind of expected here. Right?
Nice.
And, maybe I say, well, I'm not too interested in this one anymore. I can just delete that and still have my step response. And I can compare that with the last run. And, again, everything looks pretty much the same.
All right.
All right, so the next thing I want to do is actually create a feedback controller for this. And typically if you've done controls in the past, that might take a little while, but with Simulink I could do that in about 2 minutes.
Oh yeah?
Yeah, let me
All right. Excellent.
Let me drag in my PID controller block. And I'll connect my reference signal.
Yeah.
And I'll feed back.
And which library did you grab this from?
This came out of the continuous library.
Okay.
So there's some advanced features with the PID controller that I'm going to show that aren't part of Simulink. They're part of Simulink control design. It's a little bit more functionality than what's in the block. But the block itself, if you're doing PID control, you don't need to have your own custom block to use PID control. You can just grab this PID block.
Yeah.
You can choose a number of different forms of PID controllers. It could be a proportional integral, proportional derivative controller.
Mm-hmm.
And you can choose continuous or discrete time. I'll do discrete time because typically controllers are discrete time.
Okay.
I put it in as 100 hertz.
Yep.
I'll apply that change, and then I'll just tune the control system using my magic tune button, which is part of Simulink control design.
And you know what I like about what you just did? I mean, you just switched to discrete time, and now you're going to have a hybrid subsystem, a hybrid model.
Yep.
In Simulink. And all you had to do was click that discrete time button in order to get that. So, I mean, that's pretty powerful stuff. You got your discrete time controller and your continuous time plant model,
Yep.
And you didn't have to do a lot to get that to work.
And so when I hit the tune button, I get my PID tuner. And this is going to allow me to change my parameters. I can look at control parameters. I won't get into too much detail here. We do have a PID Control Made Easy webinar you can view to learn more details about how this functionality works.
Now, can you change those sliders again? Because I was talking.
And this is my favorite part.
Yeah, this is one of the best things.
So it's actively changing as I move the slider. So I can say, well, maybe I want a faster response or I want a slower, more robust response. I'll leave it at default for now.
And so each time you do that, it's changing the PID parameters, right?
Yeah. So when I hit OK, now I've got all these parameters set in my PID block for the proportional integral derivative gains and the derivative coefficient.
Yep.
And I hit OK, and I'll run that simulation. And we see that we're now controlling the system to that step response.
Right.
All right, so I think maybe that was a little bit more than 2 minutes, but I think that's a pretty quick way to get that
I'll give you a couple
tuned.
of minutes here and there. That was good. That mostly is because I was talking. It took long.
Right, and so the great thing about Simulink, again, is with the simulation, maybe there's some more complicated dynamics going on.
Yeah.
So here, maybe there's a trigonometric function. And let's see, I want my math operations. And maybe there's something a little bit more complicated going on with that spring. And, I have my controller tuned, and I look at how it compares. I say, well,
still
maybe
looks pretty good.
It still looks pretty good, but maybe I want to make some changes here, and I can see. I want to show my port label here. So now I want to see how this is actually looking over time as I'm actively working with the model.
Right.
And
so you just right-clicked on the signal and said show the value label port. So this is so that you wouldn't have to put scopes in your model for each signal that you want to monitor.
Yeah.
Right.
Well, this is going to be really, really useful for me when I'm running this in this kind of quasi-real time. So I don't like to use the term real time because that implies something a little bit more complicated if you're doing hardware in the loop testing or something like that. But I can use this pace block from the aerospace block set.
So this is the one block you're grabbing outside of the Simulink library.
Right. And this will let me run so that every second of simulation time is a second of clock time.
Okay.
And so we see that the simulation is running slower now, and I can see my results here. And so when I change this, I can update the reference value, and I can see how that changes over time. Right, and using this is going to be a little bit easier for me to see what the actual value is of that signal, instead of seeing what the value is on the scope, where it's a little bit more difficult because of the resolution of the axis.
You could see how this would be very useful if you're tweaking your model, you're trying to figure out why certain behavior might not be happening the way that you would expect. You add some of these, port value displays on your model, and you could monitor everything in one view. That's pretty nice.
And what I didn't like, though, is it's not getting quite to that step value that I want, right? So I put in 0.5, and it wasn't really getting there as fast as I wanted it to.
Yeah, it's a little sluggish.
So I just coming back to my PID tuner, And I'm just making it quite a bit faster. It's still stable here, so
Yeah.
you know, if I was worried about things like my margins or control characteristics, I can, you know, take a look at those while I do the tuning. But I'm not worried about that for this webinar, so I'm just going to make it really fast.
Okay.
And you know, we have similar tools for doing signal processing or filter design here as well that make it just as easy as this tune button does for control design.
Yeah, that's a good point. Yeah, so Simulink is used, you know, for controls engineers and folks doing signal processing. And actually, what's nice is you could use the tool to do both things within the same model. So that's pretty
exactly.
Nice.
And so here, you know, I'm just changing the value.
Fast.
Yeah, this looks a lot better. So I think I'll stick with that design.
Yeah, that's much faster than what you had before.
All right, so now the next thing I'm going to do is I want to actually have my system move up and down with my keyboard strokes.
Okay.
And
how are you going to do that?
To do that, I will come into my friend Cole's library. Cole built this library full of blocks that he uses to, you know, show people how Simulink works, and he does a lot of Simulink examples. So he's got all these great blocks that he uses that kind of do interesting things that aren't available in the base Simulink library. And one of those things he got off the file exchange is this keyboard input.
Okay.
And so in his library, I can just drag this over. And, you know, the reason you'd use a library here is so that anytime Cole makes a change, it will propagate automatically to my model here.
Oh, that's nice.
So if he made a change to this keyboard input block, then it would automatically be propagated in my model.
Right. Right. Yeah, so you don't have to constantly look for updates and see if things have been changed. I mean, you could lock it down too, though, if you want to.
Right, exactly. Either way. And it's really dependent on what you're trying to build.
Yeah.
And, you know, as I mentioned, I came to the file exchange, or Cole went to the file exchange to get that. So I just hit the community button. And you'll see we have all of our blogs here, MATLAB answers if you have a question. And maybe you don't want to call tech support. Maybe you want kind of a community-oriented answer. That could be your best answer, too, because they'll try to give you something fast and efficient. Or you can come to the file exchange, and this is where we got this model from for the keyboard input. It's from the file exchange.
Yeah, there's a lot of information to go through there.
Yeah, and you can just get there right from this community button, right in the MATLAB desktop. So if I come back to my system and I want to figure out what my up and down signals are, it's going to give me an ASCII value, right? So it's going to be, you know, some number represents those keyboard strokes. So what I want to do is I want to comment out my blocks. Whoops. And I want just this one block here. And I'll uncomment the scope. So what I'm going to do is I'm just going to run the simulation. And, it actually, you know what? I forgot to bring in the file that this block runs. So this block, getting it off the file exchange, it's got this S function, which I think it stands for a Simulink function.
Yes.
So what I need is this file that it's going to run, and it's running just a little bit of code. And that little bit of code is what's going to grab the keyboard input. So I actually want this keyboard input.
And this actually brings up the point that if you've got existing code that you want to bring into a Simulink model, this is the way you would do it. You would put it inside of a Simulink function and then use that code, and then a block represents that code in your model. So that's really what's going on here.
Let me open this up. Let's see. Oh, it must be off screen.
Oh, figure one.
Figure one. Where is it?
See, this is the resolution thing.
Yeah, resolution. So let me find that real quick.
Oh, I could help you with that.
Sure.
You right click in here. Right click there, go move, and then do that.
There we go. All right, so let me try that again.
Yep.
And I need my system up here. Okay, simulation is running. And I'll enable the keyboard inputs, and I'll just hit the up a couple times and the down a couple times. I'll disable the input, stop the simulation. And so the way this block works is it outputs a default value of 43. And then whenever you hit the keyboard button, it will output the ASCII value of that. So here, you know, I hit the up button a couple times, and that was 30. And then I hit the down button a couple times, and that was 31. And I can just zoom in a little for you.
30, 31. Yeah, got that. And you do the 43 one?
The 43 is the default, so it's going to output some value.
Oh, just I was thinking just to zoom in.
Oh, yeah, sure.
So
sure.
Yep, there you go.
Default
43.
value,
Yep.
43. So what I can do is I'm going to say, okay, so if my value is, if value is greater than or equals 30, increment by 0.1.
Yeah.
If value equals 31, decrement by 0.1.
Yeah.
Else do nothing. Right? And
Yep.
so there's a bunch of if-else blocks in Simulink I could use to do this. But what I'd much prefer to do is just be able to write that out and have it give me a better visual representation, because as this kind of builds up over time, you can imagine just how many blocks or how complicated this logic could get if I'm starting to say, well, what if my value equals 43? What if my value equals 51, et cetera, et cetera?
Yeah. We start doing some if, then, else, if type of stuff. Yeah.
So what I can do to help make this a little bit more visually simple for me to understand and a little bit easier to build is I'm going to actually use state flow and a state flow chart to build this control logic. And so state flow is another add-on, right? So it doesn't come with Simulink, but it's a great way to build up logic for a system like this. Okay, and the first thing I'm going to do is bring in a initial wait state here. So I'm going to just wait for input. And to come into my chart, I need to grab this little arrow here and drag it into the wait state.
That's your default transition. That's your starting point.
And so when I come in for my starting point, I want my output value to equal 0.
Okay.
I think I use the curly braces for this, right?
Yep.
Okay. And I'll next want to build up all that if-then-else logic. And I can actually do that very easily by adding a pattern to the chart. If, else, as I wrote out before. And it's just loading. It's going to give me some options. Or actually, I think it might have shown off screen again.
Yep.
Let's see. So I'll just move that.
Doing the trick.
Yep.
This is the thing with these resolutions when they're smaller.
Yeah.
They usually go off the screen like that.
Okay, so I'm just going to say this is going to be my up-down logic. I just like to write it all in camel case because I'm always very careful about putting spaces in. So if my value in equals 30, I want my value out to equal value out plus 0.1. If my value in equals 31, I want my value out to equal my value out minus 0.1. Else, I want my value out to remain the same.
Now, the way you have it, the output's all going to echo to the MATLAB command prompt. Do you want to do that?
Oh, no. So let me...
yeah, it's just like MATLAB, right?
As a MATLAB user, right, you get used to not being able to be a little bit dirty with your code. But I'll avoid doing that. And it'll run a little faster, I think. And actually, that means I should probably put that here. Right, okay, so what it's going to do, and I can clean this up a little bit too, is it's going to come into the chart, and it's going to wait for an input, and the way it's going to do that actually is I'm going to say, I believe it's, so I can just put in has changed from, I just hit tab and it gives me this autocomplete, and I want val in. And as I mentioned before, that original value is 43. And
okay, so that's just saying if the value is changing from its default value, then enter into this flow chart. Flowchart, you have. Otherwise, just stay in the wait for input state. This is nice and efficient too, because if nothing's changing, then all these if-then-else conditions are not even gonna.
Yeah. So every time step, it's going to come in. It's going to be in this state. If nothing's changed.
Right.
It's just going to stay in the state. It's not going to process everything every loop.
Yep.
And again, you know, something like this, you look at it, you say, well, that's not too complicated. But, you know, anyone who's worked on a big system before understands there's going to be a lot of potential for some very complicated logic, and you can see the value in not having to process all of that.
Right.
And I can do an update diagram by hitting Control D. And that's just going to process all my blocks and check that everything's okay before it runs. And we see a lot of different dialogues popped up. But what's important is it gave me a warning and an error here, like it did before in Simulink, saying, oh, you have these 2 new values you didn't define.
Right.
And so what Stateflow will do is it will guess kind of what you want for the chart. So here it says val in. That looks like an input. So it says
right
data
on
scope's
input.
input. Yeah. But val, it guessed wrong. And, it's doing the best it can, but it didn't know that this was an output, so I add the output there.
Mm-hmm.
And so now that error should be resolved. And now if I do an update diagram again, I think, let's see. Oh, I actually need to make a change for my has changed from. And actually, I need to put this into square brackets because it's logic.
It's a condition.
Yeah, conditional. Right, and I don't actually need the
right
semicolon. There we go. So you see the color change because it realizes this is a function. So now if I do my update diagram, and it's just compiling the model, getting ready to run. Looks like everything's okay.
Mm-hmm.
Come up here, I see that now I have an input and output port.
Make that stateflow chart a little bigger.
Yeah.
There you go.
There we go. Okay, so I've got my logic here, and my system down here.
Yeah, so you basically have it annotated, which is nice.
Yep. And so now if I hit enable my keyboard input, now if I hit up, we start to see those are incrementing by values of 0.1 every time I hit up, and it's going to decrement every time I hit down. And actually, if I come into this chart, we can actually see that visualized while it's running in the chart, right? So if I hit up, let's see, I need to come back to my keyboard input. If I hit up, we see that it's going around the outside if path. If I hit down, it comes around this inner in path. And if I hit just any other value, right, it's just going to skip all that logic entirely.
That's the most powerful part about using Stateflow is the animation. It really helps with figuring out the behavior of your logic.
And we see as it's running, it's not actually doing anything until I give it an input.
Mm-hmm.
Oh, and now we've got the results too. So let me disable my keyboard input. And now we can see all those up and downs, how that's reacted over time.
Nice.
All right, so I think that's about all I had to show. I put a lot of stuff in today, so if anyone has any questions about anything we've shown today, or you want to learn more, you can visit the website.
All right, thanks.
All right, thanks for watching.